Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. This is a part of the graph theory section of the lectures, and this lecture is on bipartite graph and their cycles. So the goal of this lecture is to prove one theorem. So what we would like to prove is that if G is a graph, then G is bipartite if and only if each cycle of G has even length. So it's a characterization of bipartite graphs. What I will do along the way is I will define and review, if you've already seen it. In fact, I've had previous videos about some of these vocabulary, what graphs, multigraphs, and general graphs are, what bipartite graphs are, what walks, paths, and cycles are, what distance in graphs means, and in addition to the proof of the theorem, I will also talk about trees and forests for a second. But I have a whole video on trees. I have another video on vocabulary if you want more detail. So a simple graph is just a pair of sets. It's a bunch of vertices and a bunch of edges. So the vertices is V is a non-empty set of vertices. For example, maybe it could be 1 through 7. And so I would think of those as nodes. And then there are some edges between them. E is a possibly empty set of edges, and each edge is a pair of vertices. So we can think of elements of E as subsets of size 2 of V. So for example, in the example that I have here, E is these pairs of elements. 1, 2 is an element because there's an edge between 1 and 2. 1, 3 is not because there's no edge between 1 and 3. 6, 7 is an element here because there's an edge between 6 and 7. A multigraph is a graph with repeated edges. In that case, your edges will not quite be a set, will be a multiset because there will be repetitions. And a general graph is when you allow not only repeated edges, but also loops. And in that case, your edges will not just be pairs of vertices, but will be multisets themselves. So some more vocabulary. If you have a general graph, then if you have a sequence of edges that go from one vertex to another, so x0, x1 is one edge, and x1, x2 is another edge, and so forth, and they share the vertex x1. If you have a sequence of edges like that, that's a walk of length m joining x0 and xm. Sometimes we just give you the edges. Sometimes we give you the vertices. The point is you start with a vertex, you go through an edge to another vertex, through another edge to another vertex, through another edge to another vertex. So for example, if you go from 4 to 9 to 6 to 8 to 9 to 6 to 7, then you have a walk from 4 to 7. And again, in a walk, you can repeat edges and you can repeat vertices as well. If the beginning and the end are the same, then we say the walk is closed. Otherwise, we say the walk is open. This one is, for example, an open walk. A walk that has distinct vertices is called a path. So for example, if you go from 4 to 9 to 6 to 8 to 3 to 2 to 7, then that's a path. Now, again, here I'm just telling you what the vertices are. If you want to write the edges would be the edge 4, 9, then the edge 6, 9, then the edge 6, 8, then the edge 3, 8, then the edge 2, 3, and then the edge 2, 7. The edge 2, 7 and the edge 7, 2 are the same. So it doesn't matter what order I say them. If you have a closed walk with distinct vertices, just like a path, but closed, then that's a cycle. So for example, if you start at 4 and go to 3, go to 2, then to 1, 6, 10, 9, and then back to 4, then you have a cycle. Then no repeated vertices or repeated edges. If you're going to repeat an edge, you will also repeat a vertex. So when you say distinct vertices, that means that there's no edge repeated either. So paths and cycles are sort of more efficient. You're not going through any vertex or edge twice. A cycle then has no repeated edges or vertices, starts and ends at the same vertex, and the length of it is the number of edges. In the case of the cycle, it's also the number of vertices. Now, what's a bipartite graph? So if you have a simple graph or a multigraph, then it's called a bipartite graph if you can split the vertices into two sets. So if the set of vertices can be partitioned into two sets x and y, partition means that all the vertices go into either x or y, and there's no intersection. So x union y is all of V, and x intersection y is the empty set. But that's not enough. It also has to be that all the edges of G have one end in x and one end in y. In other words, there's no edges among the vertices in x and no edges among the vertices in y. If you can do that, then your graph is bipartite. Not every graph is bipartite, but if you can figure out a way of saying, okay, these guys are the x's, these guys are the y's, and look, there's no edges among the x's and no edges among the y's, then you've got yourself a bipartite graph. Now, for that reason, a graph with loops, a general graph, can never be bipartite, because as soon as you have a loop, no matter where you put that vertex with a loop, there will be an edge from that part to itself. Multigraphs, the ones that have multiple edges, could be. So if G is bipartite, then sometimes instead of writing vertices and edges, which is what we usually do for graphs, vertices and edges, we tell you what the vertices are and the edges, we might write it as X edges Y, where the vertices are X and Y, where if you want to emphasize the parts and tell you what the parts of the bipartite graph are, we might write it like this, with one part of the vertices at first, and then the second part of the vertices there, and the edges in the middle, and reinforcing the fact that edges go from X to Y. Bipartite graphs come up often, for example, in matching problems. Like, for example, if you have a set of tasks and a set of volunteers, and for some of those volunteers are qualified for some of the tasks, then you can model that using a bipartite graph. You put the volunteers on one side, the task on the other side, and then you put an edge if a volunteer is qualified for X, and then you've got a bipartite graph. All matching problems tend to have a bipartite graph in the background. Here's another example of a bipartite graph. Take the set with 5 elements, 1 through 5, bracket 5, and let X be subsets of size 2 of 5, and Y be subsets of size 3 of 5. And we say that there's an edge from A to B if A is a proper subset of B. So for example, here what it would be. At the bottom here, I have subsets of size 2 of 1 through 5. I didn't put the curly brackets or the commas, so this is the subset that has 4 and 5 in it. And up here are subsets of size 3, and this 4, 5 is inside 1, 4, 5, 2, 4, 5, and 3, 4, 5, and therefore it has edges to those. So this is a bipartite graph. Another vocabulary that you should know about is complete bipartite graph. So you have a set of M vertices, let's call that L for left, maybe, and R is a set of N vertices, and every vertex in L adjacent to every vertex in R. So you put edges between every vertex in L and every vertex in R. If you do that, the resulting graph is called the complete bipartite graph on M and N vertices, and it's denoted by K sub M comma N. K sub N was the complete graph on N vertices. When you have N vertices and connect every one of them together, K sub M comma N is the complete bipartite graph on M and N vertices. You have M vertices on one side, N vertices on the other, and make all the connections between them, but no connection among the M and no connection among the N. So for example, K23 is this graph. There's 2 vertices on the left, 3 vertices on the right, or 2 vertices on one side, 3 vertices on the other, and there's all the edges between them. And here's K33. A cycle of length 3, there's a cycle of length 3. Is that bipartite or not? It's not. No matter how you partition the vertices, you'll have 2 on one side and 1 on the other, and the 2 together, there will be an edge between them. So there's no way to think of this as a bipartite graph. On the other hand, C4, the cycle of length 4, is that bipartite? It might not quite look like it is, but it is if we redraw it. So if we put V1 and V3, the 2 opposing vertices on the one side and the other 2 opposing on the other side, then we see that all the edges go from one side to the other, and there's no edges on the side of X and no edges on the side of Y. So cycle of length 4 is bipartite. More generally, odd cycles are not bipartite, even cycles are bipartite. That will follow from the theorem that will prove, so I don't need to rigorously convince you of that yet. I need the notion of distance in a graph. So if you have a general graph and you have 2 vertices, the distance between them is the length, that's the number of edges, of the shortest walk from one to the other. So you figure out what's the fastest way to go from V to W, and you count the number of edges you need. That's the distance. If you can't go from V to W, then that distance will be infinite. And that distance we denote by d of v comma w. So d of v comma w is the distance between v and w, is the number of edges in the fastest way that you can go from v to w, in the shortest walk from one to the other. So for example, here's a graph. What's the distance between u and v? Now there's various ways of going from u to v. You could go from u to this vertex, to that vertex, to that vertex. That would be a path of length 3. But you can also just go to x and then v, and then that's a path of length 2. So that's the fastest way. So the distance between u and v is 2. The distance between x and y is actually 1 because there's actually an edge between them. So you just can take that edge. There are more roundabout ways to get from x to y, but to find the distance, you always find the most efficient way. Now, let's say something's about shortest paths between two vertices. Let's say you have two vertices in a general graph, and the shortest walk from V to W is always a path. Because the shortest walk, you are allowed to repeat vertices, but that's inefficient. If you want the shortest walk, you've got to eliminate those side trips that you might take and come back and just go directly from V to W. So the shortest walk is always a path. And here's the lemma. Let's say that you have a shortest path from V to W, and then you pick some vertex on that path. Now, the portions of the path from V to U and from U to W are themselves shortest paths. Why is that? Shortest paths from V to U and from U to W. So going from V to U, there might be another path from V to U with the same length, but there can't be a shorter one from V to U. Because if there was a shorter path from V to U, then we would have taken that shorter path and find your way to W faster than you already did. So if you already have a shortest path from V to W, all along the way, you must have used a shortest path from V to every one of the points on that path. And by the way, we say a shortest path as opposed to the shortest path, because there may be several paths that are equal length. But the distance will be just one number because whatever that shortest path is. Okay, so now we're ready for our main theorem. If you have a multigraph, it's bipartite if and only if every cycle has even length. So this is a wonderful theorem, because if you want to check if a graph is bipartite, if a graph walks through the door and I want to know if it's bipartite, if I want to use the definition, I've got a lot of work to do. I've got to pick different x's and see if they work or not. And that's lots of checking. But this theorem says that all I need to do is look at the cycles and see if I can find any odd cycles. If I can find any odd cycles, the graph is not bipartite. If I can't, then it is bipartite. And by the way, this shows that any odd cycle is not bipartite and all even cycles are bipartite. Okay, so there's two proofs, if and only if, and usually in combinatorics, one direction is more straightforward than the other. So if the graph is bipartite, so there's an x and a y, and all the edges go from x to y, why is it that the only cycles that we can find, possibly, maybe there are no cycles, but if there are no cycles, then we're good too. But if we find a cycle, then its length has to be even. Why is that? Well, any cycle will have to start somewhere, and it will have to go, to get back to that place, it has to go back and forth between x and y. Maybe you start in x and go to y, then come back to x. Then you go, if you go to y, you have to come back. If you go to y, you have to come back. And so every time you go to y, you come back. So that's two edges that you add to your cycle. And so you start at some place and you keep adding two edges, and you got to do them in increments of two, because if you go to y, you've got to come back to x. And therefore, because you're adding a number of twos together, the final length will be even. Now, for the other direction, if a graph only has cycles of even length, why is it bipartite? Assume G is a multigraph and each cycle has even length, and we want to prove that G is bipartite. Now, first we make a simple point that the graph might not be connected, but if it's not connected, then it has different connected components. And if we can prove that every connected component is bipartite, then the whole graph will be bipartite. Because if this part is bipartite, that part is bipartite, then these different connected components don't have anything to do with each other, and therefore it's enough to prove it for one of them, and therefore it's enough without loss of generality to prove that to assume that the graph is connected. Connected again means that you can walk from every vertex to every other vertex. Okay, so where are we? We have a connected multigraph right now. Each cycle has even length, and we want to prove that it's bipartite. So how am I going to prove that the graph is bipartite? Again, all I know is the graph that walked through the door has cycles, and maybe that doesn't have any cycles. But if it has cycles, they're all of even length, and I want to convince you that it's bipartite. Well, I have to give you the parts. I have to give you x and y. And in fact, this theorem, the proof is nice because it gives you an algorithm for finding x and y, the two parts. And you start with picking your favorite vertex u. You pick one vertex, whichever one you like. You call that u, and you define x and y. What is x? X is going to be all the vertices whose distance from u is even. That includes u, by the way, because the distance of u from u is 0, and therefore it will be an x. So u will be an x, but everything else whose distance from u is even will be an x, and y will be all those guys whose distance from u is odd. And in this case, then we know that x and y partition the graph, because if you have any vertex, its distance from you is either odd or even, because the graph is connected, all the distances are finite. And so every vertex will be in one part, and the distance can't be both even and odd. And so the intersection of these two sets is empty. So what remains to be proved is that this actually works, in the sense that there's no edges in X or Y. So we have to show that if A and B are in X, or A, B, or Y, then AB is not an edge. So this is sort of the picture we have. If A and B are in X, U again is in X, and if A and B are also in X, we have to show there's no edge between them. Now, if A can't be connected to U, there can't be an edge between U and A, because then the distance between U and A would be odd. But two other ones, we have to convince ourselves there can't be an edge either. Now, the two proofs, whether or not A and B are in X or in Y, are the same. In fact, I will sort of say generally for both of them, but we can in one sweep show that AB is not an edge if A and B are in the same part. So again, we are in a connected multigraph. We have an arbitrary vertex. We have picked our X and Y, and we have picked these two elements A and B in one of the parts. X is all the vertices whose distance from U is even. Y is all the vertices whose distance from U is odd, and A and B are either in X or in Y. I'm going to ask you to choose a shortest path from U to A. I mean, the graph is connected, so you can do that. And I also want you to pick a shortest path from U to B. The first thing I will want to claim is that the edge AB is in neither one of these two paths. It's not sitting there. First of all, and so why is that? So let's just prove that for one of them. The argument is the same for both of them. So here's the shortest path from U to A. Why isn't the edge AB anywhere there? Well, because if it was, first of all, it couldn't be in the middle, because if it was in the middle, this would not be a path, it would be a walk, and we could shorten it. So it has to be at the end. If the edge AB is anywhere in this path, it will have to be that last one. But if that's the case, that the distance from U to A would be one more or less than the distance to B. In this case, when I'm looking at the shortest path from U to A, the distance from U to A would be one more. And the reason for that is that the path from U to B here is also a shortest path, as we discussed in the previous slide. So this is a shortest path. Maybe it's not the one that we were thinking of before, but it will have the same length. And so therefore, the distance between U and A and U and B will be off by one. But that's not possible, because both these distances have the same parity. They're both even or they're both odd. And so they have to differ by at least two. And so that's a contradiction. So AB is not an edge on any one of either one of these two paths. So what? So again, X and Y are defined. X are all the vertices whose distance from U is even. Y is all the vertices whose distance from U is odd. A and B are in one of the parts, are either in X or in Y. And we have a shortest path from U to A, and we also have a shortest path from U to B. Now we want to assume what happens if AB was an edge. Remember, A and B are the ones in one part. We're hoping that AB is not an edge, but what would happen if AB was an edge? AB, we already know, is not on one of these two paths, but maybe AB is just an edge off by its own. And if you think about what we already proved, we know A and B do not appear anywhere on those two early paths at all. But it could be that maybe AB is an edge. If that's the case, then look at the last common vertex of the two paths, the two shortest paths from U to A and B, because they started at U. They might have some edges in common. They might come together, leave, and so forth, but there's a last place they come together because they're ending up in different places in A and B, and call that Z. So Z is the last common vertex of these two shortest paths, one from U to A and one from U to B. Now, these two paths from U to Z will have the same length. They might not be the same, but they will have the same length, because if one of them was shorter, then that would mean that we didn't really find a shortest path from U to B or U to A. So again, when you have a shortest path, every point along the way, the path to that is a shortest path. And so these paths from U to Z, both of them will be shortest path. They might actually even be the same, the path, but even if they're different, they will have the same length. So if that's the case, then look at the cycle that goes from Z to A, and then for that extra edge AB, and then back to Z, this red cycle here. What can we say about that? Well, I claim that that's a odd cycle. And the reason for that is that the distance from U to B and U to A were both even or both odd, because A and B were in the same part. The distance between U and B and U and A have the same parity. They're both even or both odd. And when we subtract this distance from U to Z from both of them, we're subtracting the same number from two even numbers or the same number from two odd numbers. And so this distance from Z to B, this path from Z to B and the path from Z to A will again have the same parity. They both will be even or both will be odd, because we took two things that have the same parity. Same parity means both even or both odd. And we took the same number, subtracted the same number, and we were left with two numbers that have the same parity. And if you add two numbers that are even or two numbers that are odd together, you will get an even number. So the length of going from A to Z to B is even, because there's two numbers that have the same parity been added. But then there's that one extra edge, and that one extra edge makes for an odd cycle. And that completes the proof, because we showed that if two vertices in the same part, the same X and Y have an edge between them, then there must be an odd cycle. So if there are no odd cycles, if all cycles are even length, then AB cannot be an edge, and therefore the graph is bipartite. What did we prove? We proved that if you have a multigraph, then it's bipartite if and only if each cycle of G has even length. So that was the proof that we just did. Remember now, I have a whole video on trees. A forest is a simple graph with no cycles. A tree is a forest with one connected component. So a tree is a connected graph with no cycles. Now, if you have no cycles, then you don't have any cycles. And that means all your cycles are even. So a corollary is that if G is a forest or a tree, then G is bipartite. Forests or trees are automatically bipartite. This is the end of this lecture. Like or subscribe to my channel if you want to be subjected to videos like this. Keep hydrated at all times, and I will see you in the next video.